What I erased, I'm just gonna draw again. And that is the template that we're gonna use over and over again to to restore homeostasis. So we must always begin with a signal. We always begin with a signal, also known as stimulus. And the signal and the stimulus detects either an increase plus or a decrease. A decrease off of what? An increase off of what? Homeostasis. So this stimulus will not come out unless there is a deviation in the homeostasis. That's stress. The drop is a stress. Hypo, that's a problem. Hypo. And increase, hyper, that's too much. We don't want that. We don't want too much. We want U. We want to restore homeostasis. That's known as U or U. So when we look at each variable, it's always going to be U. So we begin with 1. That's step number 1. Step number 1 is the signal, the stimulus. What is step number 2? Step number 2 is the input. Excellent. That's an input. But what kind of input is it? That's a sensory input. Sensory input signal. And that's step number 2, sensory input signal. What about number 3? What happens in number 3? Then there's going to be a computer, a control center. A computer or a control center that will integrate the problem and initiate positive feedback or negative feedback. How do we repair homeostasis? With positive feedback or negative feedback?
Negative feedback.
There's going to be negative feedback. Then that's the integrator. Integration. Also known as control center. Control center. The control center receives an input and generates what?
An output.
An output. Excellent. Now describe this output for me. What kind of output? It's a motor. That's a motor output. The motor output signal. That's a motor output signal. The motor output signal will always and absolutely be what? The opposite of the input. That's how we have negative feedback. My input, I'm going too fast. My output, I gotta slow down. I'm going too slow. My input is I'm going too slow. My output, let me go fast. So always there is a opposite relationship. There is a direct inverse relationship between input and output if I am doing negative feedback. But if I'm doing positive feedback, then they're not going to be opposite. Like in birth, when a baby is being born, the baby push, the uterus push some more. So here the input is the baby push, the uterus push some more. In the milk ejection, the baby suckles the breast milk. The baby suckling the breast milk, irritating those nerve endings. I forgot one thing. You see, I knew I forgot it. What is it? The sensor. The sensor who sends the signal. You see, no matter how long you do this, you're still going to make a mistake. There's a one in the middle, right here. So let's squeeze it in. That's number 2. Who's number 2? So why did you stop me?
So I was going to wait till you finish to see if it adds up to the 8.
Okay. All right. Sensor. Number 2 is the sensor who senses the signal. Is the sensor or the detector. Detector. The sensor could be an osmoreceptor to detect the osmolarity. It could be a chemoreceptor to detect the chemistry changes. It could be a pressure, pressure or stretch receptor. It could also be a thermal receptor. That's 2. Then the signal is 3. The integrator control center is 4. The output, who will be always opposite to the input, that's going to be 5. Then we're going to have an effector. So the effector is going to mediate, the effector is going to mediate the effects of the negative feedback. And then we're going to restore or green, homeostasis. That's what we need, homeostasis. Then we have restored our homeostasis. When we restore homeostasis, then we have to stop. So that's 5, that's 6, that's 7, and 8 is stop. Okay, I'm sorry. You got to stop talking while I'm teaching. So we're gonna have to stop or terminate the response, because if you keep going on and on and on, now you're gonna reverse the stress. So your friend was talking about the thermia. So now let's look at the loop for thermia. So let's begin with the patient. So what is our euthermia? So now we can tell our deviation. Our euthermia, where we belong, our euthermia, what is our euthermia? Our euthermia is 37 degrees Celsius. If we go 2 up, that's red, that's hyper. If we now become 47 degrees Celsius, that's too high, that's too high, that's hyperthermia. That's hyperthermia, too high. And if it drops too much, now that's no longer euthermia. Now that's a drop, minus. That is now known as hypothermia. That's hypothermia. So now these are 2 separate scenarios. That's scenario number 1 and that's scenario number 2. So let's begin with scenario number 1. One patient is really hot. You're really hot. So the temperature went up. So what's the signal? What's the stimulus? Hyper or hypo?
Hyper.
So that's hyper. That's number 1. Number 2, who's gonna detect the input sensor signal and send it to the integrator? Who's gonna be the sensor, the detector? Is it the osmoreceptor?
No.
Is it the chemoreceptor? Is it the pressure stretch receptor? Is it a thermoreceptor? Thermoreceptor. So the thermoreceptor is going to send an input sensory signal to the integrator control center. In this particular example, it's the hypothalamus. And in the hypothalamus, there's a nucleus called the thermal nucleus of the hypothalamus that deal with that. You know, the police, they have a division for robbery. They have a division for homicide. Same thing in the hypothalamus. There is a nucleus to regulate thermal activity. There is a nucleus to regulate pH. There's many nucleus to deal with different variables. So here the hypothalamus will say, I have an input that the temperature is so high. So my output has to be to make the temperature low. So now the output motor signal is going to be drop the temperature. And who's going to be the effector? The effector is going to be my sweat glands. So you're going to be sweating. And when the sweat glands receive stimulation, output stimulation, they're going to restore homeostasis. And we said not only the sweat glands, also the blood vessels. So the blood vessels dilate. They vasodilate. Why do the blood vessels dilate? When they dilate, then a lot of blood is flowing to the surface. A lot of blood is flowing to the periphery. And the hot blood, we said already in the diffusion that we have movement from an area of a high concentration to an area of a low concentration, from an area of a high thermal activity to an area of a low thermal activity. So your blood is hot. It's so hot. Your air is cool. So now the blood is flowing to the periphery, and the heat is flowing from your body into the air. So when heat is leaving your body into the air, are you going to become more hot, or now you're going to be cooler? You're going to get cooler. And when you're going to get cooler, your temperature, when you get cooler, your temperature is going to drop. You're going to get to homeostasis. Then you stop sweating. You don't keep on sweating, and now you're going to get cold. And then you have restored homeostasis. Don't worry about the details. Just appreciate the general picture. Now let me go do hypothermia. That was hyper. You see, both are in red. Both are bad. Both are stress. So now we're dealing with hypothermia. So hypothermia, a drop in temperature, is going to be this signal, the stimulus, a drop in temperature, hypothermia. Then number two, who's going to detect hypothermia? Is it an osmoreceptor, a chemoreceptor, pressure receptor, or a thermoreceptor? It's going to be a thermoreceptor. The thermoreceptor is going to be sending an input sensory signal that, oh, temperature is dropping, temperature is dropping. So the integrator is going to be the thermal nucleus of the hypothalamus, and it's going to send an output signal that is negative feedback or positive feedback? Negative feedback. And that is going to be going to an effector. Number one, your blood vessels. When you're so hot, the blood vessels dilate or constrict? When you're so hot, they dilate. When you're so cold, constrict, because you want to prevent the dissipation of heat. Imagine you're so cold and your vessels are dilating. So now the little heat that you had is now going away. So you're going to freeze to death. So now you're going to vasoconstrict. So that's the first effector, your blood vessels. Then, the second effector, your skeletal muscle. We talked about how energy shuffles and moves from one form to the other. We talked about how in the car you put gasoline, that's chemical energy. Then you start the car, the ignition, then the gasoline is going to be an explosion. So the explosion is going to make the pistons in the transmission start moving. And then you're going to have heat energy before kinetic energy. So the gasoline turning into heat energy, good. An explosion and the heat thermal energy is moving the pistons, the rotor is moving. Then when the heat is pushing against the pistons, then what happens is your wheels start spinning. Then you shuffled energy from chemical into heat into mechanical. Then when you're so cold, your brain is going to send action potentials. Action potentials are a form of electrical energy. The action potentials are going to get to your skeletal muscle. And the skeletal muscles, when they receive the electricity, what's going to happen? When you get the electricity, what's going to happen? You shake, right? So now they're going to send electricity. They're going to make your skeletal muscles start shivering. And when you shiver, you convert kinetic energy into ATP, which is a chemical energy. And that ATP, chemical energy, you use it like fuel, like Bunsen burner. Like you use it like a form of fuel that you burn to make yourself warm. And we call that shivering thermogenesis. Excellent. Genesis is the making. So that's shivering thermogenesis. Shivering thermogenesis. Now we use shivering thermogenesis forever or only till we get homeostasis? Only till we get homeostasis. And when we get homeostasis, what happens then? We stop. So now, am I gonna want you to know all the details? All I want you to know is that to appreciate that we have this 8 steps, and the 8 steps, you know, the football team, there's a quarterback, there is a running back, there is a receiver, but do you have the same quarterback in the 2 teams, on 2 different teams? So here, the integrator for thermia is going to be different than the integrator for glucose. Hyperglycemia is going to be different from the integrator for calcium. Calcemia is going to be different from the integrator of the acids and bases. So these, but we're going to use the same template. We're going to use the same steps to restore homeostasis. Now, let's now talk about what we are here for, and that is the acids and bases. You have to develop an intuition of what is an acid, what's a base. Back in the day, an acid, oh, that's vinegar. Okay, that's not detailed enough. We need to know exactly what is an acid. So an acid is a substance that increases hydrogen proton concentration. Is a substance that increases hydrogen proton concentration. So an acid increases hydrogen proton concentration. So an acid equal a high acid equals high hydrogen proton concentration equals low pH. That's the one that you really need to know. Okay? What's the relationship between pH, acid, and hydrogen proton? If the pH is low, then the acid is high and the hydrogen proton is high. So in fact, the pH equals negative log of the hydrogen proton concentration. The pH equals negative log the hydrogen proton concentration. So what does that mean? That means if you go from pH 7 down to pH 6, you increased hydrogen proton by 10 times. If you drop from 6 to 5, you increase hydrogen proton by 10 times, plus 10. If you drop from pH 5 to pH 4, you increase hydrogen proton concentration by 10 times, x 10. If you drop from pH 4 to pH 3, you increase the hydrogen proton by 10. What if you go the other way around? If the pH goes up by 1 unit, then you drop the hydrogen concentration by 10. If you go from 4 to 5, you drop the hydrogen proton by 10. If you go from 5 to 6, you drop the hydrogen proton by 10. That's what the log is for, that we're going by 10 order of magnitude. So it's a huge drop when your pH, that's why in your body, if your blood pH goes from 7 to 6, oh, you're dead a long time ago. So the hydrogen proton increased severely. You really got to know this one, that the acid go up when the hydrogen proton go up, but the pH goes down. So don't think this patient is acidic, their pH is so high. That's wrong. Their pH is so low. So pH has really low. The acidity has really low. Hydrochloric acid is the most acidic. It has pH 1. That's the worst acid. That's in your stomach to help you digest. Mechanical digestion, churning the food, cutting the food. Okay, and then enzyme digestion, that's in the intestine. But in the stomach, there is some chemical digestion, but usually the major chemical digestion that takes place is in the intestine. That's where you separate big sugar to small sugars. You go from lactose into galactose and glucose. That's the sugar of milk. You go from then you go from maltose, sugar of oatmeal and grains, into 2 glucoses. We're going to get to that. And then you go from sucrose into glucose and fructose. So that kind of digestion, that's chemical. That's chemical digestion. Okay. So the pH, we use HCl for digestion. That's really acidic. I mean, you don't get more acidic than that. And who's the most basic is sodium NaOH. That has pH of 15. That's the highest. And who's right in the middle? 7. If 1, you need to know those 3. Who has a pH 1? HCl. Who has pH 15? NaOH. That's the biggest base, NaOH. Who's the biggest acid? HCl. Who's right in the middle? 7. Who's right in the middle? I'm sorry? Somebody said it. Alkaline is when you're basic. So NaOH is basic. So sodium hydroxide is really basic. HCl is really acidic. Who's right in the middle? Who is at 7? No, we're not at 7. We are 7.35 to 7.4. Is water. Water is right neutral. Neutral in the, I heard it. That's why I said I heard it. Somebody said water, but then they refuse to. They plead the fifth. Okay, so it's water. It's in the middle. Okay, is our pH neutral? Our pH is slightly
Base.
Slightly more basic.
Slightly basic, yes, slightly basic. Very good. So now we know we know what acidic is. What about basic? Basic means low hydrogen proton, means high hydroxyl OH, and it means pH high. You need to know this one. You need to know this one, that basic means low hydrogen proton, high hydroxyl, and high pH. Okay, so basic means low, because acidic means high hydrogen proton. So basic means low hydrogen proton. Very good. Then OH,
Increase of base.
very good. And pH is, and the pH is high. So now, yeah, high hydroxyl. So OH is known as hydroxyl. That's the functional group. We'll get to that. Hydroxyl. Hydroxyl. Yes.
I have a question. So NaOH is NaOH 15 is pH, like average?
At 15, that's the highest. That's the end of the spectrum. So 1 is hydrochloride. That's the end of the spectrum. That's really acidic. And 15, that's the end of the spectrum over there. That's really basic. NaOH, sodium hydroxide. That's the really basic. And right in the middle, the tip of the seesaw, that's water, 7. Our blood is, you need to know that one too. What your pH of the blood. Can't be going around not knowing your own blood pH. You have to know the pH of your blood. So that's how you're going to know the range to find out if it's the pH is too high. So how are you going to know if the pH is too low or if the pH is too high and you don't even know the pH of your own blood? So the pH of the blood is, the pH of the blood is, the pH of the blood is between, the max is 7.35, that's green, and then is 7 point, I'm sorry, the max is 7.45, the minimum is 7.35. You go less than that, that's red hypo. I'm sorry? That's the blood pH level, the green one. Between 7, if you're playing around here, if you're going up and down here, you're healthy, you're good. You're not in the emergency room if your pH between 7.35, 7.36, 7.37, 7.38 up till 7.45. That is normal healthy pH. Below that, that's hypo. That's minus. The pH went down, and we don't call that hypo pH. We don't call that hypo. Yeah. Yes.
Alkaline
and acidic. Yeah. So when we drop down, that's acidic. When we drop down, that's acidic. When we go up, that's basic. That's too basic. If we go up, that's too basic. That's hyper. So now let's see how your body repairs both. How does your body repair? Alkaline, yeah. Basic is alkaline. Basic is also alkaline.
Do you use alkaline or do you guys use basic?
Yeah, that's two. Yeah, basic and alkaline, both. We can use both. Okay, all right.
You're supposed to stay in the middle of 5, right?
You're supposed to stay in the middle, 7.35 to 7.45.
But there's a level in the middle, right?
This whole level is okay.
Oh, that's the middle.
Yeah, that's the middle, yeah. Okay? Yeah, that's all fine. You can be anywhere here.
I think it's because you see you have the basic and the top, that's why.
Hmm?
I think
No.
you have basic.
Yeah, it's not in the middle. Our pH of the blood is not at 7, it's not water. It's slightly basic.
Right.
Slightly basic, as Christopher was saying. It's slightly basic. So our pH is not in the middle. Okay? It's not 7. It's not 7.
Right, but if you go to the doctor and they're saying, they look from the 7.45 down, if you pass 5, then you're acidic, I guess, or something?
If you pass this, you're acidic. If you're
Oh,
below
okay,
this,
okay.
if you're below this, you're acidic. If you're
Okay, I was...
okay, you guys are recapping with each other. You guys are recapping what's happening in the movie? Okay, all right. So now, let's repair both. Let's repair both. Let's repair pH. So now we're not dealing with thermia. Now we're not dealing with no thermia. We're dealing with pH. Okay, so now the pH is 7.45. That's the highest. And 7.35. That's the lowest. Let's begin with this patient here. That's patient 1. Now that patient is suffering from acidosis. So acidosis means high what? Hydrogen proton concentration. It means pH low. It means OH decrease.
Because it's a P.
It means OH decrease. pH decrease, hydrogen proton increase.
What's OH?
OH is for basic. That describes for us the basicity. We drew over there OH with hydroxide. That's why sodium hydroxide, NaOH. That's the highest basic. Yes? Okay. So acidosis means high concentration of hydrogen proton. It means low pH. It means low OH. That's for acidosis. For basic up here, it means low H plus. It means basic. Basicity is high, and the OH is going to be high. So OH is high for bases, OH is low for acids, H plus is low for bases, H plus is high for acids, pH is low for bases, and pH is high for acids. pH is high for acids. So let's repair this guy. Acidosis. Did you get it? Yeah. Okay. Let's begin with acidosis. pH is low. That means hydrogen proton is too much. The signal for too much hydrogen proton. That's the signal. Too much hydrogen proton. Who's going to be the sensor, the detector? Is it an osmoreceptor? Chemoreceptor? Yeah, chemoreceptor. That's hydrogen proton. That's the chemoreceptor. Then the chemoreceptor is going to send an input signal saying, an input sensory signal saying that there is a high hydrogen proton. Hydrogen proton. So the integrator here, the hypothalamus, will send this an output signal to, if high hydrogen proton input, what's the output going to be? Why are you talking about OH? We're talking about H plus. We're talking about H plus. Hydrogen proton too high. Repair that. Hydrogen proton is too high. So the output is going to be? Yeah, the hydrogen proton. So the output is going to be the opposite of the input. If the input high H plus, the output is going to be to drop down the H plus. So who's going to be the effector? The urinary system. That's one effector. So now H plus. So when I say it's acidic, the blood is too acidic. So much H plus in the blood. So now the kidney is going to start taking H plus from the blood, throw it in the urine. Too much H plus in the blood. We're acidic. Let's get rid of H plus. So the kidney is one effector. Then the lungs. They're going to say, let me remove carbon dioxide, because carbon dioxide creates a lot of H plus. So now you're peeing a lot of H plus and you're expelling, throwing out a lot of carbon dioxide. Then there's another buffer system, and that is the amino acid. So the amino acid has an alpha carbon with north, south, east, west. 4 terminals. North, south, east, west. So in the north, you have hydrogen proton, then you have an amino terminal, then you have a carboxylic terminal, and then an R group. Don't worry about that. What you need to worry about is that the buffer system, when there is too much hydrogen proton, the OH will start to take it. Say, I can take some of that. So the amino acid has 2 sides. One side for when you have too much H plus, you say, I'll take some of that. And sometimes when you have such a very low hydrogen proton, the other side, NH3, will say, I have 3, I'll give you 1, and now it becomes NH2. So that shows you the buffering capacity of the amino acids. The amino acids, when there is so much hydrogen proton in the blood with one terminal, they take it. The OH will say, give me OH, give me H. I'll take H's from you. I'll help you out. And if there is little H plus, the other side, NH3, will say, I can give you some H plus if you need. And then the other side gives you. So just appreciate that the amino acid is like a buffer. You have a lot of H pluses, you want to get rid of them? The carboxylic terminal will take the H's. And if you have a little bit in your blood of H plus, the amino terminal will say, I'll give you some. So that's called buffer capacity of the amino acid. Yes?
That's basically what I was going to ask. So like, what happens when it's too low?
Yeah. Yes?
What happens when the OH is too high?
When the OH what?
When the OH is too high?
It doesn't work that way. This doesn't work with the OH. You work with the H's only, the H plus. So if the H increase, you're acidic. If the H decrease, you're basic. So that's how we repair the things, not with the OH.
So what happens when the H plus is low? It moves from the urinary.
Yeah, so now we're going to do that now. So we were dealing with H plus too high. So now let's do the opposite. So actually you had a good hypothesis. What do you think is going to happen?
It moves from the urinary system back to the blood.
Excellent. That's exactly what happens. And what about breathing? Your lung is going to start sucking carbon dioxide from air. What is it? It's gonna slow the respiratory rate to suffocate you some more. You're not gonna suffocate, but you're gonna decrease the rest. So now let's look at that. Now we're not dealing with this no more. We're dealing with basic. Basic means H plus low, OH high, pH high, acidity low, and basicity high. So the signal will be low H plus. The input sensor signal will be low H plus. The sensor is chemoreceptor. Then the chemoreceptor will go into the integrator control center, and it's going to cause effects, outer effects that are opposite. I mean, at this point, you really have to know that the input will always be the opposite of the output in negative feedback. So then what's going to happen is the kidneys are going to stop taking hydrogen proton from your blood. It's going to keep it there. In fact, it's going to take from the urine, throw it back into the blood, and your breathing rate is not going to be hyperventilation. It's going to be hypoventilation. You're going to breathe less. And finally, you're gonna your buffer system is now gonna not take hydrogen proton. It's gonna give hydrogen proton, and then you're gonna reach homeostasis. Then you're gonna stop there. Yes.
When
When
the blood is very acidic.
the what?
When blood is very acidic and it moves the H plus to the urinary system, is that when your urine is more darker?
Is more what?
Is that when your urine is darker?
Is that the urine what?
Is that when your urine is darker?
The urine is darker if there's red blood cells. So that means the patient has kidney failure, and then the red blood cells start leaking in the urine. But your urine will be acidic. When they look at it, it will have so much H plus. That's called urinalysis. Very good. So we do urinalysis to see no protein is supposed to be in the urine, because the kidney is supposed to be so good, so efficient to return hydrogen proton back into the blood. So if the kidney is not doing that as well as it should, then you will see, due to kidney failure, that protein making its way into the urine. Yes?
But does the color change at all with the acidity?
The color does not change with the acidity. The color does not change with the acidity because hydrogen proton is colorless. It's not going to change. But it's going to change with red blood cells. It's going to change with some problem in the metabolism of iron. When you're breaking down some disease that is hemolysis, breaking down red blood cells. Yes? I'm sorry. Say again?
I was just like recapping. I was saying so only when there's like a failure that involves blood, that's
Exactly. Yeah. Okay, and yes?
So it has nothing to do with hydration?
So hydration, water is basic, so hydration is gonna elevate the acidity. So it's very good to drink water because our blood is slightly basic, but most of the stuff we eat is acidic, like the carbs are acidic, milk is acidic. Okay, fruits, yeah, acidic too. Yes.
I think what he means, when you drink less water, urine tends to be more yellow, but when you drink more water, it's like a paler yellow.
Yeah. So when you drink water, but that also has to do with the protein content. It also has to do with, but yeah, I don't know if it's gonna. I don't really know, honestly. Like I haven't looked into that. All I know is that how they shuffle around. But I'm gonna look into that. What's the relationship between your blood and I mean, if there is if you drink a lot of water, you're gonna increase water volume in your blood, so you're gonna be peeing more water than often. It'll be lighter in color. But if you don't drink a lot of water, your urine is gonna be concentrated. It's gonna have a little bit of water. That's why it comes out really yellow. But it's not because of the hydrogen plus.
Says the acid make your urine yellow? Away from
It's not the acid, it's the depletion of water. Because your body is dehydrated, it's gonna look really concentrated.
Oh.
So it's concentrated. Because of the urea is so concentrated. But because if you have enough amount of water, it's gonna dilute the urea.
Urine's going to be acidic.
Okay? Alrighty. I want to end with a very important concept, and that is the isotope. What's an isotope? What is an isotope? An isotope is, so we have to have the Niels Bohr model in our mind. What does a nucleus look like? Obviously the Niels Bohr model. Niels Bohr model says that you have electrons spinning, and then you have a nucleus. Inside the nucleus you have P for proton, N for neutron. This is Niels Bohr. B-O-H-R, Bohr. Okay? So what did Niels Bohr say? Niels said that in the nucleus we have a proton and a neutron. So what's the atomic number then? The atomic number equals equals the number of protons. So these are the same. Not protein, protons. Proton. So the atomic number is the number of proton. And the atomic mass equals the number of protons plus the number of neutrons. Together, the number of protons plus the number of neutrons. So that's the atomic mass. Now, if we look at hydrogen, why do they call it a hydrogen proton? Is it positively charged?
No,
It is not positively charged.
added another proton.
No. The hydrogen proton has one proton and zero neutron, no neutron. Then this is hydrogen. Then there is deuterium. Deuterium is another isotope of hydrogen. Well, if you're an isotope, that means you also have the same number of protons. You can... No, these are atoms. So deuterium is an isotope of hydrogen. Hydrogen has one proton. What's the atomic number in the periodic table of hydrogen? 1. So if you want to be an isotope, you gotta be 1. We can't change that. Because if you add another one, you have 2. Now you're helium, you're no longer hydrogen. So isotopes will always have the same proton number. So deuterium has 1 proton, and tritium has 1 proton. They all have the same number of protons. But the difference is, hydrogen has 0 neutrons, no neutrons. Deuterium has 1 neutron, and tritium has 2 neutrons. So what is the atomic number for hydrogen? 1. What is the atomic number for deuterium? 1. The atomic number is is the proton number only. The proton number only. So the hydrogen atomic number is 1. Deuterium atomic number is 1. Tritium atomic number is 1. Now look at the mass number now. What is the mass number for hydrogen? 1, because 1 plus 0 is 1. So now hydrogen has the same atomic number as the mass number. Deuterium has an atomic number of 2. I'm sorry, deuterium has an atomic number of atomic number 1. It has a atomic mass of 2, and tritium has an atomic mass of 3, because 1 proton plus 2 neutron. So an isotope is different variations of the same atom, different variations of the same atom. Now, some of you were having a problem last week understanding. I'm recording this. I'm going to post it to you on my YouTube channel. You're going to watch it there. Just pay attention now. Okay. I didn't want to tell you that so you don't relax. Yeah, I didn't want to tell you that.
You never gave us the YouTube channel.
Okay, I'll give you my YouTube channel. Okay, everybody, please remember, everybody, look. So, a lot of you were having a problem last week understanding how in the periodic table, this number, the number below, the number below each molecule, that gram, like for example, sodium has how many grams underneath sodium? Look at the periodic, please pull out the periodic table. 22 point something. That 22 point something is what? It's not atoms. That 22 is the molecular weight. Molecular weight of what? So for example, you said atomic mass? No, not atomic mass. That's the molecular weight. So what does that mean? That's a mole worth. So if I have a dozen of eggs and a dozen of cars, what more do I have? The same.
They're both the same. It's just the mass is different.
Exactly. So in the periodic table, you cannot have a dozen of sodium and a dozen of potassium. But you have a mole. You got to know that number. So Avogadro's number, you got to know Avogadro's number. Avogadro's number is 6.03 times 10 to the power of 23. I mean, that's the number 6, not with 3 zeros to the side, not with 6 zeros, not with 9 zeros, 23 zeros. So they did that for every single element in the periodic table. Bring Avogadro's number worth of sodium, weigh them. How much that come out to? Then they wrote it in the bottom, below it. Bring Avogadro's number's weight of all of these potassium. Then weigh that. See how much does it weigh, then record it. So it's a standard number. It's like a dozen. But it's for the atoms. That number, you cannot have eggs in this number. I don't think a whole earth has this number of eggs, with Avogadro's number worth of eggs. Is that point clear? Is this point clear? How are these weights in your periodic table gotten? They collected a mole worth. That's a mole's worth. Yeah, so a whole mole, which is Avogadro's number. Then I posted for you a game show question that said, what is Avogadro's law? What does Avogadro's law say? Avogadro's law says if we have two chambers and we put the piston to make the pressure in chamber 1 equal to the pressure in chamber 2, then the volume of chamber 1 equals the volume of chamber 2. What's going to happen now, no matter what atom you put in there, sodium, if you put in chamber 1 sodium, in chamber 2 potassium, chloride, helium, calcium, they're going to equal in the number of moles. Which is very interesting because they don't weigh the same. They don't have the same number of protons. They don't have the same number of neutrons. They're not isotopes. They are different atoms. But he realized if you equate the pressure in two chambers, if the pressures are equal, if the volumes are equal in a chamber, then the molecules inside them will equal no matter how different they are in the atomic number or the mass number. Any questions? Any questions? Yes? Okay, I'll tell you my YouTube now. Okay. All right.